Welcome to the deep dive. Today, we're jumping right into the core of modern automated data centers, really getting into the nuts and bolts.
That's right. We're looking at the architecture behind these high-scale fabrics, specifically EVPN, VXLAN, and the brains behind the operation, Juniper Apstra.
And our source material is a bit unusual today. We're actually drawing from the framework of the JN0-481 certification exam questions.
Yeah, but think of it less like exam prep and more like a super condensed map of the absolutely essential technical concepts.
Exactly. Our mission here is to take those really dense, critical pieces of info and translate them into, accessible insights for you.
We want you to get the foundational understanding, the why behind these designs.
We're definitely not here to quiz anyone. It's about the operational wisdom. And just for context, this kind of exam, it's pretty demanding, 90 minutes, 65 multiple choice questions.
It demands real precision.
And that precision is what we want to unpack for you today. Okay, so let's start in the bottom layer, the physical structure, or at least the routing underlay. These modern data centers, they almost always use a spine and leaf close fabric.
Right, the standard two-tier topology.
And for the routing underneath, the best practice usually points towards external BGP, eBGP. Why eBGP specifically? How's that set up?
Well, eBGP brings a certain simplicity and predictability. You don't have the complexities of redistribution you might get with an IGP like OSPF or ISIS.
Okay.
Path selection is clearer, and the setup rule is straightforward. Every single leaf device peers directly with every single spine device.
A full mesh between the tiers.
Exactly. Creates that simple two-hop routing domain.
That sounds like potentially a lot of links, though, and a lot of IP addresses just for those point-to-point connections. Is there a way to be more efficient with the addressing?
Oh, absolutely. Efficiency in the underlay is crucial. The standard best practice here is using very small subnets for those links, typically unique 31s or sometimes 30s.
Ah, the 31 trick. Just 2 IPs needed.
Precisely. It saves a ton of address space, obviously, but maybe more importantly, it keeps the control plane lean. You avoid the overhead you'd get managing adjacencies in a larger IGP setup.
And troubleshooting is easier.
Much easier. The path is explicit, predictable.
Okay, so the eBGP underlay gives us that simple, scalable, efficient foundation. But, a flat high-speed network isn't enough. We need segmentation for different tenants, applications.
Right, you need to carve it up. That's where VXLAN comes into play. It's the overlay.
The overlay network. And the key mechanism there is the virtual network identifier, the VNI.
Exactly. The VNI is what allows us to create all these separate virtual networks running on top of that single physical IP fabric.
I remember the old days being stuck with VLANs and that 4,000-odd limit.
Yeah, the 4K limit was a major bottleneck. The VNI fundamentally solves that scaling problem. It's a 24-bit identifier within the VXLAN header.
24 bits. That's a lot more.
It's huge. Over 16 million potential segments. Compare that to the 4,096 VLANs. That's the game changer for modern multi-tenant data centers. It identifies each specific layer 2 or layer 3 virtual network running over our eBGP underlay.
Massive scale, got it. But scale introduces other challenges, right?
Yeah.
Like mobility. EVPN, the E in EVPN stands for Ethernet VPN. That seems to address mobility and keeping things consistent.
Yes, exactly. Think about what happens in, say, a virtualized environment when a VM, an endpoint, moves from one host to another, potentially connected to different leaf switches.
Yeah, the network needs to know where it went. In the old world, that could cause chaos, right?
Yeah.
MC flapping.
Precisely. MC flapping the network, seeing the same MP address appear rapidly on different ports. It could lead to forwarding loops if not handled correctly. And in these fabrics, we're not running spanning tree protocols, so we need something smarter.
So EVPN has a built-in fix for this.
It does. It uses BGP, the same protocol we're using for the underlay, but with EVPN extensions. Specifically, there's something called the mMobility Extended Community attribute. It's carried in the EVPN Type 2 route, which advertises MXC addresses.
Okay, that's a technical mouthful. What's its core job?
Its job is actually quite elegant. It carries a sequence number. Think of it like a version number for the MXC addresses location.
Ah, so when an endpoint moves, the new leaf switch advertises the MAC with a higher sequence number.
Exactly. Every BGP speaker in the fabric sees these updates. By comparing the sequence numbers, they know which advertisement represents the latest, most current location for that MSC address.
So it's like a built-in conflict resolution directly in the routing update.
You got it. It automatically suppresses the older information, preventing those forwarding loops and mitigating the disruption from MC flapping. It's essential for the dynamic, virtualized environments we run today. It makes mobility seamless.
Very clever. Okay, let's shift gears from the fabric protocols themselves to the conductor of this orchestra, Juniper Apstra. It's an intent-based networking system, an IBN.
Right. It's about defining the outcome you want, the intent, and letting the system figure out the configuration details.
So if Apstra is defining the intent, what the network should look like, and how it should behave, where does that definitive master plan actually reside?
It resides in one place and one place only, the Apstra server.
So it's not just a dashboard or a management tool?
No, it's much more fundamental. It's the single centralized component that holds the entire blueprint. It's the brain.
And people often call it the source of truth. Why that specific term?
Because it maintains the absolute authoritative record of everything. The original network intent, the actual operational state it discovers from the devices, and all the resources like IPs, ASNs, VNIs that have been allocated.
So if the real network drifts from the plan?
Apstra knows. It constantly compares the intended state with the actual state and flags discrepancies, or even automatically remediates them, depending on the configuration. It is the single source of truth for that entire fabric.
Okay, let's walk through how Apstra builds this network conceptually. It starts with abstracting the hardware, right? Handling the physical box identity separately from what job it does.
That's right. Before you even say, this switch is a spine or this switch is a leaf, you define its raw capabilities using something called a logical device.
A logical device, like a template.
Exactly like a template. It specifies the vendor, the hardware model, maybe the OS version, and crucially, things like interface capabilities, can this 100 gig port be broken out into 4x25 gig? That kind of detail.
But it doesn't say if it's a spine or a leaf yet.
Correct. That's the key point. The logical device is purely about the physical characteristics. It's reusable. It separates the hardware identity from its role in the network topology.
Why is that separation useful?
Agility. And avoiding vendor lock-in. You can design your network architecture based on roles and capabilities, and then plug in any physical device that matches the required logical device template. Makes hardware swaps or adding new gear much simpler.
Okay, hardware is abstracted. Now let's talk services. We mentioned that huge pool of VNIs earlier. When a tenant needs a virtual network stretched across, say, 5 different leaf switches, how does Apstra make sure all 5 leaves use the same VNI for that same virtual network?
Consistency is key here, and that consistency comes from resource pools.
Resource pools, like a central bank of identifiers.
That's a great analogy. Apstra manages pools of resources, VNIs are a prime example, but also VLAN IDs, autonomous system numbers, ASNs, IP address ranges. When you define a service like that stretched L2 network,
The virtual network in Apstra terms.
right, Apstra automatically allocates the necessary VNI or VLAN or IP subnet from the appropriate resource pool.
And because everyone pulls from the same central pool.
You guarantee consistency across the fabric. No accidental overlaps, no manual tracking errors. Every leaf involved in that service gets the same VNI assigned from that central managed pool. It ensures the intent is implemented identically everywhere it needs to be.
Makes sense. So Apstra handles the main configuration through this intent model. Logical devices, resource pools. But networks are never perfectly clean, are they? What if you need a small, specific config snippet on just 1 or 2 devices? Maybe a custom firewall filter or a unique BGP policy that doesn't quite fit the standard model.
Yeah. Reality always bites. There are always those corner cases. Apstra handles this through a feature called configlets.
Configlets. Little bits of configuration.
Essentially, yes. They're small targeted pieces of raw device configuration code like Juniper Junos commands or Cisco NXOS commands that you can apply to specific devices or interfaces on top of the configuration generated by Apstra's intent engine.
So it lets you inject custom commands without breaking the whole model.
Exactly. It gives you that escape hatch for necessary customizations, providing flexibility without forcing you to abandon the benefits of the centralized IBN approach for those small, unavoidable tweaks.
Useful. Okay, configlets handle the exceptions. What about the normal change process? Managing updates. Let's say I've designed my network, it's running, and now I want to make a change, add a new virtual network, maybe modify an existing one. I make the change in the Apstra UI, but I haven't hit deploy yet.
Yeah.
What's the status of that change within Apstra?
That change enters the staged state.
Staged. Meaning?
Meaning it's part of your active blueprint, your design, but it hasn't been pushed to the physical devices yet. Apstra has calculated the necessary configuration changes, rendered the commands, done all the prep work. It's sitting there, reviewed, validated internally, ready to go, but not live.
It's like the final confirmation screen before you commit.
Precisely. It's the last checkpoint before impacting the live network.
But sometimes, even with staging and checks, deployments go wrong. You push the button, and suddenly something breaks. Critical application goes down. What's the "oh no" button? The immediate rollback mechanism.
This is one of the most powerful aspects of a true IBM system like Apstra. The feature is called Time Voyager.
Time Voyager. Sounds dramatic.
It kind of is. If a deployment causes problems, Time Voyager lets an administrator instantly revert the entire network fabric configuration back to a previous known good state. You choose a specific prior commit ID.
Like a snapshot in time.
Exactly. A snapshot of the entire network's intended configuration and the associated device configs. You pick that commit ID, hit restore, and Apstra rolls everything back to precisely how it was before the problematic deployment.
Not just one device, but the whole system state managed by Apstra.
The whole system state relevant to that blueprint. It's a comprehensive, audited rollback capability. It drastically minimizes mean time to recovery, MTTR, when things go wrong. It's a huge safety net.
Incredible. Okay, last piece of the puzzle. The network is deployed, hopefully successfully. How does Apstra continuously check that the network is actually doing what the intent says it should? It uses something called intent-based analytics, or IBA probes.
Right. IBA probes are like automated continuous health checks and validations. They're constantly verifying that the operational reality matches the defined intent.
And these probes need data from the network devices themselves, counters, states, routing tables, all that. Which part of the IBA system is responsible for actually grabbing that raw data from the switches?
That responsibility falls to the collector. Each IBA probe definition includes specifying what data needs to be collected, and the collector component within the Apstra system is what reaches out to the devices using agents or protocols like netcon gRPC to pull that specific operational data.
So the collector gathers the facts.
And then the other parts of the IBA probe analyze those facts to determine if the intent, like is this link utilization below 50% or is this BGP session established, is being met. Building on those ideas of staged changes in Time Voyager, the real, maybe subtle innovation in IBM isn't just the speed of automation.
Okay.
It's in formalizing the process of safe failure and auditable recovery. Think about it. How many other complex IT management systems that you use daily have a truly integrated, full system rollback feature, one that can revert the exact state of every managed component back to a specific point in time?
That's a good question. Usually rollback is partial or manual or messy.
Exactly. That formalized safety net, that ability to confidently try changes knowing you have a clean, comprehensive undo button that is a quiet revolution IBM brings. It changes how you approach network evolution.
Something to definitely think about in terms of managing complexity and risk. Thanks for joining us for this deep dive.